Do you know the many surprising connections between the deepest parts of space and the deepest recesses of our ocean? Both are cold, dark places where humans cannot breathe and where the pressure alone is enough to kill you. Both upset our normal experiences of gravity, providing explorers with a strange weightlessness or buoyancy if they could somehow survive being there in the first place. And both contain many unsolved, captivating mysteries. Our oceans are filled with life we've never seen before. And who can say what lurks in the unexplored corners of space? I was initially caught off guard when I heard that NASA had turned its attention towards exploring the hadal zones deep in the ocean. After all, NASA is normally about space. What are they doing deep under the water? And on Earth? I'm Alex McColgan and you're watching Astrum. Put on your diving gear and join me in a world of undersea facilities, uncanny life, and an environment so hostile we've mapped more of Mars than of this terrain on our own planet. In 1957, a year before NASA was founded, a paper published by the Journal of the Royal Society of Arts claimed the deep oceans covered over 2/3 of the surface of the world, and yet more is known about the shape and surface of the moon than is known about that of the bottom of the ocean. This was a reference to the fact that in the world before echo-sounding technology was commonly used to map the seafloor, we didn't know much about the topography of what was down there. We've come a long way since then, but while we have mapped the moon thanks to satellites and telescopes, we have still only mapped 23.4% of the ocean floor in high resolution. In fairness, this still represents an area of 120 million square kilometers, about 3 times the moon's surface area, so the old saying no longer holds entirely true. Hence why we can instead talk of Mars, which has a surface area of 145 million square kilometers. But still, it's a profound gap in our knowledge of our own world. NASA was founded in 1958 with the purpose of expanding human knowledge of phenomena in the atmosphere and in outer space, and developing vehicles and technologies that would help them to do so. Exploring the ocean was not originally on their radar, or sonar. However, in 1978, NASA began monitoring the ocean with their first dedicated oceanographic satellite, CSAT, which was capable of collecting data on sea surface winds, surface temperatures, wave heights, and other features. This helped them learn more about our planet's oceans and their impact on the global climate. Still, some of NASA's most exciting forays into the ocean only began at the turn of the millennium. One way in which the sea can prepare astronauts for space is through simulated space experiences. About 8.7 kilometers off Key Largo in Florida is the world's only undersea research laboratory, Aquarius Reef Base. Built in 1986, it is a small, 3-roomed habitat large enough to house 6 people at a push, with a main room that combines sleeping and living quarters, an entry dock, and a wet porch for entering the sea around it. It was originally designed to help aquanauts remain at the bottom of the sea for weeks at a time through a technique known as saturation diving. By remaining at the depth of 19 meters, the human body becomes saturated with gas dissolved in its bloodstream, which allows these researchers to stay at depth without ill effects for much longer periods of time, 9 hours for one dive rather than 1 or 2 hours. This made it ideal for biologists wanting to study the local environment in situ. In 2001, however, NASA, along with other space agencies such as ESA, realized that it made a great space training location. The cramped living conditions mimic those found on the International Space Station, so astronauts who spent a week at Aquarius Reef Base would get a vital taster of what life would be like up there. It also allowed them to practice performing experiments and generally get used to the expected and unexpected aspects of life in a hostile environment. NASA began the NEMO program, or the NASA Extreme Environment Mission Operations, and that same year began sending their astronauts to the habitat. There have been 23 NEMO missions since then, merging astronaut crews from a variety of different space agencies, which lasted up to 3 weeks. Astronauts there became aquanauts and got the chance to don deep spacesuits, getting a taste for what spacewalks might be like outside of our planet, readying them for the day humans return to the moon or go to Mars. This was not the only use NASA had for the ocean, however. Perhaps the most significant training was not for NASA's astronauts, but rather for the machines that would one day visit the largest oceans outside of planet Earth. Let's now go deeper and consider the exploration of alien oceans. Our solar system is home to many large oceans outside of Earth. Jupiter's moon Europa and Saturn's moon Enceladus, to name just two, have significant bodies of water beneath their kilometer-thick icy surfaces. In spite of only being 1/4 of the Earth's diameter, scientists believe that Europa holds twice as much water as all of our oceans combined. This is an intriguing concept, as even though no sunlight penetrates down to those depths, the mixture of liquid water bordering a rocky inner crust would make both of these locations ideal candidates for life. Scientists have considered how to best test to see if life really has arisen in the oceans of icy moons. In 2024, NASA will launch the Europa Clipper, with the mission to fly by the moon Europa and scan it to learn more about the depth of its icy shell, to try to determine the composition of its oceans and generally get a better picture of the moon as a whole. However, Europa Clipper will only be laying the groundwork for future missions, which one day might see cryobots melting through the 10-kilometer thick icy shell of Europa using nuclear-powered radiators to penetrate its oceans and see firsthand what lies below. Once down there, no radio signal will be able to reach them easily. Messages will be relayed via a vast cable brought down through the ice along with the cryobot. This means that such cryobots will need to be able to autonomously descend a further 100 to 200 kilometers to explore the dark, chilling, and highly pressurized environment they're likely to find, to see what alien life might swim in those waters. So, with a mission objective on the horizon to explore deep, dark waters in search of never-before-seen life, what better place to start than the unexplored oceans we already have at home? The deepest parts of the oceans on Earth are only 11 kilometers deep, but due to the gravitational differences between Europa and Earth, the pressure you'd experience between the two are much more comparable than you might think. Europa's 100-kilometer deep ocean is thought to have a hydrostatic pressure between 130 to 260 megapascals, which, if it existed in an ocean on Earth, would equate to a depth of around 13 to 26 kilometers. This is much better than if you'd had to go hundreds of kilometers down on Earth, but it's still no picnic. Pressure at the bottom of the Mariana Trench, the deepest place in our ocean, is 1,100 times the pressure on the surface, which is enough to crush the individual cells in the human body, or to implode most submarines. And yet, life survives there. And it doesn't just survive, it thrives. The deep-sea explorers of the Galapagos hydrothermal expedition in 1977, using a specially reinforced remotely operated vehicle that could survive those pressures, were shocked to discover not a barren wasteland, but thriving ecosystems gathered around hydrothermal vents on the ocean floor down there. Tube worms, crabs, and fish were found in rich abundance. As scientists performed more dives, they found all manner of strange life forms down there. Shrimp like amphipods the size of your hand, giant, ethereal, big fin squid that were 8 meters long and looked positively alien. In the depths between 6,000 and 11,000 meters, in an area known as the Hadal Zone, named after the god of the underworld, Hades, life had learned to adapt to conditions in ways no one could have imagined possible. And this incredible adaptability gives scientists a better understanding of what might be possible on other worlds. The deepest parts of the ocean are mostly found near the fault lines of continental plates, where one plate subducts under another. These deep trenches create a unique V-shaped environment that channels organic debris from above down into a sludgy pool. Whenever a carcass falls down there, the organisms in the hadal zone are somehow able to quickly detect it and arrive within minutes. Other organisms rely on nutrient-rich liquids pumped out of thermal vents. If you added up all these trenches into one landmass, you would end up with an area the size of Australia, a whole unexplored continent. NASA wants to explore these regions using autonomous drones, perhaps whole swarms of them that would be able to detect locations of interest such as thermal vents, and would be able to map out the terrain using cameras and onboard AI, similar to that used by the Perseverance rover on Mars. It's a challenging task. Not only would such a drone need to be able to withstand the excessive pressure, but the temperature around such thermal vents can spike to hundreds of degrees. Drones would need to be able to survive rapid temperature swings if they are able to survive. In 2014, one such deep-sea drone known as Nereus was sent into the Kermadec Trench off the coast of New Zealand. This is the area NASA has selected as testing ground for its new equipment. However, sadly, Nereus was not able to survive the pressure down there, in spite of having succeeded on hadal dives before, and it imploded. Pieces of plastic were later found floating to the surface. NASA's latest drone is Nereus's descendant, a smaller, lighter, autonomous submarine known as Orpheus. Orpheus has yet to enter the depths of the hadal zone. Instead, it is being put through its paces in shallower waters. But if it works, its lighter design would make it easier to transport on a rocket to the oceans of Europa at some point in the distant future. Although, this dream might not be so distant after all. In 2023, NASA's Planetary Exploration Science Technology Office gathered a team of 40 top researchers from multiple fields in the California Institute of Technology to discuss how close we might be to making this trip. A surprising amount of technology needed is already there. Their conclusion was that the mission was feasible, scientifically compelling, and the most plausible near-term way to directly search for alien life in situ on an ocean world. With the combined information being gathered by Europa Clipper and the technical experimentation being done with Orpheus and other autonomous submarines like it, perhaps it is something we will see within our lifetimes, although no concrete plans have been made yet. When it finally does happen though, and a human-made drone starts to swim in those dark seas across the gulf of space, what will it see? Perhaps it will feel strangely like home. We are water-based life forms here on Earth. The first large, complex animals formed in our oceans. All life is dependent on water to live. Rather than arid, rocky and dusty wildernesses, there will be something strangely soothing about exploring oceans beyond our own, like entering a place we already know, even though we've never been there before. Does something lurk in those alien seas? Although it's only speculation, the sheer fact that this might be true is enough. To discover that life came to exist not once, but twice in just our own solar system would have massive implications on life's prevalence in the universe as a whole. It would mean life is likely abundant, and we ought to be ready to see a lot more of it out there. But proving it is the challenge. Only by perfecting the technology here on Earth will we be able to crack open those frozen shells, enter those inky depths, and find the definitive answers we seek. For NASA, their mission to find life in our solar system begins in our oceans. The universe is a harsh, brutal place. Solar winds, high radiation, and extreme temperatures and pressures make it largely inhospitable. And yet, life found a way. It's in you and in me. And perhaps there is no quest more epic than the search for life beyond our beautiful blue home. But scanning the night sky for possible neighbors, like most things in astronomy, comes with its challenges. Where could they be? What would they look like? Should we even look for them? Are they, in turn, looking for us? One thing that makes the search for alien life tricky is that we don't know exactly what we're looking for. But by studying ancient life forms on Earth, scientists can get a clearer idea of the kind of organisms that are most likely to be out there, and where we might be best off looking. I'm Alex McColgan, and you're watching Astrum. Join me today as we uncover how scientists actually hunt for alien life, the unique characteristics of Earth's earliest life forms, and the surprising role these ancient microbes play in guiding the quest to answer the eternal question, is there anybody out there? If you were tasked with combing through a seemingly infinite universe for signs of life, where would you start? I reckon I'd start by looking for a planet similar to ours. Starting the search in the most hospitable part of the galaxy seems like a smart move. The galactic habitable zone is the region of a galaxy that has the most optimal conditions for potentially life-bearing planets to develop. Typically, it's a spot with enough heavy elements for Earth-like planets and minimal cosmic drama like supernovae or stellar close calls. This excludes stars too close to the center or in the spiral arms of galaxies, since they are full of super intense, harmful radiation. So far, we've discovered 5,539 exoplanets, of all different shapes, sizes, and compositions. Scientists are still debating what kind of atmospheres might be hiding signs of life on other planets. As far as we know, life on Earth emerged 3.8 billion years ago. At that time, our atmosphere was mainly nitrogen gas, carbon dioxide, and water vapor. You'd understand then why some scientists choose this atmospheric composition as a preferred focal point. But others aren't so convinced. They say only searching for these compounds is limiting, since methane and hydrogen gas atmospheres may themselves be signs of life. In reality, it seems to be a bit of a chicken-egg situation. The atmospheric composition of a planet determines what kind of life, if any, could emerge on that planet. But the kind of life that emerges also affects the composition of the atmosphere. Let me quickly explain with an example from home. Today, Earth's atmosphere is 21% oxygen. That wasn't always the case. It wasn't until about 2.4 billion years ago that free oxygen gas started accumulating in our atmosphere. This is known as the Great Oxidation Event. The main theory among researchers is that cyanobacteria living in the ocean evolved the ability to photosynthesize and started releasing oxygen gas faster than it could react with other compounds. Eventually, this oxygen evaporated from the oceans into the atmosphere, replacing the methane that was already there. This is an example of a biosignature of life, the next step in honing our mission to find alien life. Biosignatures are substances, signals, or patterns that could be a sign of biological activity. This could be as obvious and direct as a fossil, or something more subtle like the composition of a planet's atmosphere. They are important because they indicate not only the potential presence of life, but also the level of its sophistication. It's important to understand that all biosignatures are really just potential biosignatures, because while they could be signs of life, they could also be caused by non-living things. A big challenge scientists face is battling all the false positives that arise. There's no official classification system for biosignatures, but it's useful to think about them falling into three categories: gaseous, temporal, and surface signatures. Gaseous biosignatures are direct or indirect products of metabolic activity. The most common manifestation of this is the composition of the atmosphere. For example, the presence of haze could be an indirect byproduct of a methane-rich world. This could tell us that a particular planet hosts microbial life similar to what we had on Earth over 2.5 billion years ago, before the Great Oxidation Event. It's similar to the example we explored earlier of how having free oxygen in the atmosphere could be a biosignature for photosynthesizing life. Temporal biosignatures are time-bound changes that can correlate with biosphere activity. On Earth, the concentration of carbon dioxide in the atmosphere rises and falls with the seasons. Vegetation grows in the spring and decays in the autumn. This oscillation is way stronger in the northern hemisphere than the southern hemisphere because it has more landmass. In theory, we can use this kind of information to see where on an exoplanet life is most likely to be. However, nothing is so black and white. Temporal biosignatures can be caused by abiotic factors too. The concentration of methane in Earth's atmosphere, for example, changes mainly due to its interaction with water vapor in the troposphere. So even though the methane itself is from a biological origin, the temporal oscillations are dictated by abiotic factors. I personally find surface biosignatures the most interesting. Basically, every planet reflects some light from its star. Different materials on the surface of the planet will reflect different combinations of wavelengths of that light. This results in a unique reflectance spectrum for every material. Surface features like rocks, snow, water, and soil can all be deduced from a reflectance spectra. Life can also influence the reflectance spectra of a planet. This is an example of a surface biosignature. Here's where it gets super cool. Today, the Earth appears blue from space because its oceans reflect a lot of blue light. But some scientists think that there was a time when our planet would have been purple instead. There's an ancient family of microbes that produce a protein called bacteriorhodopsin. Bacteriorhodopsin can create energy without a carbon source, something plants can't do. It literally just turns sunlight into metabolic energy the cells can use. It is thought to be one of the simplest and earliest bioenergetic processes to have developed. But why would it make Earth appear purple? Bacteriorhodopsin contains a pigment that reflects a lot of purple light. This makes its cell membrane appear purple. An early Earth would have had oceans full of this organism, turning the whole planet visibly purple. While it's just a bit of fun to imagine a purple Earth, the implications of this theory mean that these microbes, and others like them, could be a very useful surface biosignature of exoplanets. Of course, the reflection of purple light alone doesn't mean much. But if it were to be combined with evidence of a highly saline surface, that could start to paint a more convincing picture. You see, the specific family of ancient microbes that produce this purple protein are called halophilic archaea, or haloarchaea for short. Archaea are some of the most ancient lineages of life on Earth. Even though they're single-celled organisms, they are not to be confused with bacteria. The two are actually totally different domains of life, but we won't go into that. Halophilic means they grow and survive best in conditions of extremely high salinity. Halophiles belong to a larger group of organisms known as extremophiles. Extremophiles are life forms that are able to live in very hostile environments. There are lots of different kinds of extremophiles that are well adapted to different kinds of extreme conditions, like very high or very low temperatures, pressures, dryness, radiation, salinity, acidity, and heavy metals, or any combination of those extreme conditions. These organisms span the globe, inhabiting the harshest parts of our world, from sulfuric hot springs in Japan to the Atacama Desert in Chile, to sewage treatment plants in Germany, and even a hypersaline deep lake in Antarctica, where our beloved haloarchaea were found. What makes extremophiles so interesting is their unique biology. As you can imagine, living in such extreme conditions forces you to get creative. Extremophiles' biochemistry and physiology are often modified in very clever ways to help them adapt to their harsh environments, and this makes them an astrobiological gold mine. Many extremophile habitats on Earth are surprisingly similar to conditions on other planetary bodies. These regions on Earth are called analogues, and they can teach us a lot about where we might find life beyond our home planet. For example, the Atacama Desert in South America is a very arid environment with high salinity, high UV radiation levels, and oxidizing soil, making it quite similar to Mars. In fact, we've been studying it as an analogue to Mars for years. Life has been found across the Atacama Desert, but its presence is highly patchy. In a way, this is good news. It helps scientists identify the exact factors that cause life to appear where it does, and therefore, where we might have the best chance to find it on Mars. The extremophilic yeast, Exoplanet, is another example of this. It was found in high altitude regions of the Atacama and caught the attention of astrobiologists pretty fast. Researchers were looking at how Exoplanet's protein expression changes in a simulated Martian environment. After the first 24 hours of exposure, they found some proteins were overexpressed and others underexpressed compared to baseline levels. However, there were no signs of heat shock proteins, the compounds organisms release in response to high stress conditions. Even more surprisingly, 7 days into the exposure, Exoplanet's protein expression patterns were back to normal. This is a big deal because it indicates that Exoplanet is able to recover and survive under Martian conditions. In other studies, Exoplanet showed great resilience to the Earth's stratosphere. It also showed the highest UVB and UVC resistance when compared with other similar yeasts. All this together makes it a promising model for potential life on Mars. It may be a stretch to suggest, but it is possible any Martian life we might find could be biochemically similar to this humble yeast. Certain species of Haloarchaea are also being studied as exciting astrobiological models. Specifically, Halobacterium NRC1 and Halobacterium lacus profundi. They are both extremophiles that thrive in high salinity and are great candidates for understanding potential life on Mars and Jupiter's moon Europa. Think about it. If there is a planet where conditions are totally different to ours here on Earth, it makes sense that the life we may find there could be completely different. But if the planet does have similarities to our own, is it really so crazy to think that life there might look similar too? Mars is a specific focus for our search for life because it has several similar early geological processes to Earth. Scientists have determined that Mars was possibly much warmer and wetter in its history. This suggests there could have been super salty brines on early Mars. Like we've said, these hypersaline environments are ideal for Haloarchaea. Wouldn't it be cool if these ancient microbes could have been enclosed in Martian brines, lying dormant all this time? Similarly, Europa is thought to contain salty oceans 2 to 3 times the volume of Earth's below its inhospitable surface. This subterranean ocean might also be chemically rich thanks to a silicate seafloor and surface oxidants, making it a great candidate for halophilic life. In fact, scientists have been testing this theory by shooting Haloarchaea into space since 1994, testing to see the types of harsh environments they can survive. The first mission involved the ejection of a capsule into low Earth orbit. The short-term exposure results were promising, with the microbes surviving the initial exposure. The European Space Agency then designed the EXPOSE facility for medium and long-term exposure experiments on the outside of the International Space Station. 3 separate missions were launched in 2008 and another in 2014, testing survival of various halophilic archaea strains in space. In March 2019, results emerged from the ESA's BioMex experiment. They reported that microbes from Earth survived 18 months of space exposure outside the ISS, suggesting life could theoretically survive on our neighbour, Mars. Clearly, there's still a lot we don't know about these microbes. For a start, they've only ever been studied in isolation. How would they interact with a wider environment? All the research so far has focused on sodium chloride, but how would these organisms fare in other salts? So even though they seem like promising candidates with lots of potential, more research is needed to fully understand their implications for astrobiology. So, how does knowledge of these ancient microbes turned astrobiological models help us in the search for life in the universe? Well, within our own solar system, having intimate knowledge of these organisms can directly impact where we send our space missions. For example, the Spirit rover was sent to the Gusev crater to investigate a suspected ancient lake. We already had lots of evidence for volcanic hydrothermal vents on Mars, but Spirit discovered lots of new evidence pointing to hot spring activity in Mars's past. Hot springs are great places to look for biosignatures because they can preserve ancient cells in their chemical precipitates for a long time. It would be an ideal place to find fossils of Martian organisms, if they ever existed there. Beyond the Kuiper Belt, studying extremophiles lets us better understand how life arises and evolves in the universe. Firstly, it can show us what traits to look for in distant planets, a certain spectral fingerprint, or a particular gas in the sky. It also indicates what the signals we receive from distant planets could mean about how hospitable they are. Extremophiles show us what type of life we might expect on other planets. And finally, they push back the limits of life as we know it, to redefine what is possible time and time again. Our searches for signs of life haven't been very fruitful yet, and will likely take many decades more. Designs are already in the works for a new generation of telescopes that will take to the skies in the 2030s and 2040s. The Nautilus is a concept telescope that could be operational by 2033 and would enable scientists to cover 50 times the light collection area of the James Webb Telescope thanks to its large aperture. Another concept, put forth by NASA, is designed to observe potentially habitable exoplanets around Sun-like stars. The Habitable Exoplanet Observatory, or HABEX for short, would look for biosignatures like water and methane. It would also become the first telescope with the ability to directly image an Earth-like exoplanet. They sound fascinating. I hope they get approved. We've come a long way and still have a long way to go, but we are not giving up our epic mission to find other life forms and their homes beyond the bounds of our planet. Our distant relatives will just have to wait a little longer to be found. As telescopes like the James Webb look out across the Milky Way, you might have heard the growing buzz around newly discovered exoplanets. It wasn't that long ago, only 1992, that we found the first planet outside our solar system. But since then, over 5,500 have been confirmed in the relatively small area of space, only a few thousand light years across, that we reside in. When the Milky Way itself is roughly 100,000 light years in diameter, this offers us a tantalizing promise of billions to trillions more across the rest of our galaxy. Every star on average likely has at least one planet, and perhaps has several. With all of these exoplanets out there just waiting to be found, it's only natural we would want to turn our thoughts towards Goldilocks zones and planet habitability. After all, humanity has its eye on colonizing the stars, and an Earth 2.0 is surely waiting for us out there, mathematically speaking. In fact, you might have already heard that phrase, Earth 2.0, being delivered in headlines of articles or videos claiming that a planet has been discovered that would be ideal for human life and colonization. However, don't believe the hype. All the planets we found so far have, to put it scientifically, sucked. And once you hear what I'm about to tell you, you'll agree that moving to any of them will be the last thing any sane person would want to do. I'm Alex McColgan, and you're watching Astrum. Join with me today as I give you the grand real estate tour on the potential Earth 2.0s we've discovered so far, and explain why right now is the wrong time to get onto the planetary property ladder. When choosing an Earth 2.0, just like with building a house, it's a good idea to start by establishing your non-negotiables. Some of this is fairly simple to consider. For instance, temperature. You want a nice, temperate climate, somewhere that's not too warm and not too cold. Given that temperature drops the further you are from the sun, every planetary system has a sweet spot where the temperature of a planet is likely just right. Not too hot and not too cold, similar to Goldilocks and her bowls of stolen porridge. As a rough rule of thumb, if a planet is at the right distance from a star, it may well have a suitable temperature for us to set up shop. Of course, this is in no way a guarantee. After all, Venus, a planet residing in this zone, in theory should be perfect. But its choking atmosphere makes it the hottest planet in our solar system in spite of its relative distance from the Sun compared with Mercury. So it's clear, atmosphere also plays a part in all this. Speaking of atmosphere, that's also something you'll want to look for on Earth 2.0. Ideally something with oxygen and water vapor, and without anything that would poison us, but at least something that could trap heat in and offer some protection from space radiation. However, sometimes a non-negotiable is simply the neighbors that live close by. So let's consider the first major reason why most of the galaxy's exoplanets fall short: their neighboring stars. Our own star is known as a G-type yellow dwarf, a relatively fast-burning, short-lived sort of star, at least compared to some of the other options out there. Stars like our Sun tend to live for 10 billion years before their cores collapse and they transform into a red giant. It is stable, and that stability has been useful for the life that eventually flourished here. However, yellow dwarfs are far from common in the Milky Way. They represent only 10% of the total stars. Far more common in occurrence are the long-lived red dwarfs, which make up 75% of the stars in our galaxy and can live for around 14 trillion years, longer than our universe has existed, which means we've never seen one die, so to speak. And unfortunately for the planets orbiting them, red dwarfs come with numerous drawbacks. For starters, red dwarfs have a much closer Goldilocks zone compared to their yellow cousins. They burn less brightly, with luminosities between 10% and a measly 0.0125% that of our suns. So unless you want to live on a world shrouded in perpetual night, which sounds cold and depressing to me and will make growing plants a bit of a challenge, you'd want an Earth 2.0 to be a lot nearer to its red dwarf to compensate. This wouldn't be in and of itself a problem if it weren't for the second characteristic of red dwarfs that make them very unpleasant neighbors: their instability. Our Sun is the main source of our space weather. It shoots out a frequent stream of solar winds, flares, and coronal mass ejections. However, this doesn't compare to the amount of space weather created by red dwarfs. Flares from red dwarfs can be 100 to 1,000 times more powerful than those emitted by our Sun. The frequent bursts of plasma and radiation coming from red dwarfs are powerful and dangerous enough to strip away the atmosphere and even boil liquid water on planets in the habitable zone. And given how much closer planets are to their star in a red dwarf system, the odds of life getting enough time to arise before being hit with a life-sanitizing dose of X-rays is pretty slim. If you want to live on a planet around a red dwarf, you'll likely need some serious sun cream. This rules out many known exoplanets, such as astronomer favorite Kepler 186f, which some scientists hoped might be habitable. while it may be possible to live for a time in quite uncomfortable conditions in a deep underground bunker on such a planet, the experience would hardly be pleasant. But even during periods between harsh solar weather events, there's another problem with planets around red dwarfs: their tendency to be tidally locked. Being tidally locked means that the same side of the planet always faces the star as it orbits. There is no rotation between day and night. One side of the planet is in perpetual heat, and the other side in permanent shadow. Due to gravitational constraints, planets near their sun have a tendency towards being tidally locked. Just take a look at Mercury with its day that lasts 176 Earth days, or 2 Mercurian years. This lack of rotation could render most of the planet uninhabitable. You'd either face scorching desert creating heat on the day side, or freezing ice on the night side. Even if humans tried to live in the narrow band of twilight that would ring a tidally locked planet, liquid water might prove difficult to find. Any moisture in the air that found its way to the night side of the planet would get locked there, solidified as ice. Overall, the planet would be very dry, and even in the twilight zone, there would be no rain. And that's not to mention the low power of a magnetic field that would likely be found on a tidally locked planet. The dynamo effect that powers the magnetic field on Earth is thought to be influenced by the Coriolis effect, the rotation of the Earth imparting momentum to rising and falling liquid metal in its core. Without this rotation, such a magnetic field would be inevitably weaker. So, I'm sorry to say that this rules out planets such as Proxima Centauri b, our closest exoplanet. Proxima Centauri b is otherwise an interesting candidate. Its closeness makes it one of the easiest planets to get to for us, situated only 4.2 light years away. It's thought to be a rocky, Earth-like planet, which is convenient, as living on a gas giant would be challenging to anyone with a fondness for solid floors beneath their feet. And most compelling, its mass and radius are very similar to Earth's, meaning it has a similar gravity. Why is this important? Let's compare it with another Earth 2.0 contender, Kepler 452b, the first planet to ever be referred to by that title, and the planet described by a NASA scientist as the closest twin to Earth. Kepler 452b has much to recommend it. It is orbiting around a yellow dwarf, like us, at a similar distance. This means it's in the Goldilocks zone that makes liquid water on the surface possible. However, it is a super Earth. This means it has a mass and radius combination that makes it about twice that of Earth's. When it comes to gravity, how much is too much? Some scientists researching the question put the figure at 4 times Earth's gravity, this being about the limit of what a human could survive. However, even living in just twice Earth's gravity could get rather uncomfortable. To properly visualize this, or at least get a rough approximation of it, imagine lying down, but then imagine a second person lying on top of you, putting all their weight on you. This is your night. Every night. Every breath being fought for. Come daybreak, you must lift that extra person up, haul them onto your back, and then carry them with you everywhere you go. Everywhere. And be careful not to fall, as suddenly it's much easier to break a bone. Falling downstairs is no longer painful, it's likely lethal. Everyone must do this. The elderly, the infirm, small infants trying to take their first wobbling step. Keeping this in mind, it's easy to grasp just how exhausting life in double gravity might end up being. If you're a bodybuilder or athlete, you will likely be alright, but for most people on Earth, it would be a slow torture. Your heart furiously beating to move your blood around, making it feel like you're running even when you're standing still. And if you want to triple the gravity, add an additional person on top of that. And things don't get much better going the other way. Sure, everything is much easier as that weight is lifted, However, living under reduced gravity comes with a host of health risks that we can see from astronauts who've spent just a few months on the International Space Station. Over time, the calcium bleeds out of your bones, causing them to become brittle. Your muscles atrophy. Your heart develops issues. Your immune system suffers. All told, even if you're exercising every day, your long-term prospects aren't looking good in a low-gravity environment. A fact that is challenging NASA scientists as they try to figure out how to set up human outposts on places like the Moon or Mars, where astronauts might go to live for just a few years. Humans have spent millions of years adapting to life on our planet. We're very used to how things are here. We're just not suited to anywhere else. We've not evolved to face such conditions. In some respects, it's a testament to how well we've acclimatized to the environment we were born in, but it's a big obstacle if ever we want to live anywhere else. And so, the hunt for Earth 2.0 goes on. As I mentioned, there are likely billions of undiscovered planets in our Milky Way galaxy. The odds of at least one being out there that meets our criteria for gravity, temperature, lack of life-threatening radiation, and presence of atmosphere and water are high enough to be a certainty. Actually finding one that meets the criteria is much more of a challenging task, particularly when most planets are still invisible to even our strongest telescopes, except for a brief moment when they pass in front of a convenient star and block out its light. If someone tells you that they've already found Earth 2.0, I take it with a pinch of salt. We won't ever really know that the planet is actually suitable for human life until we somehow cross the gulf of space and go there to see it in person. Of course, until we discover how to do that, it's all a bit of a moot question anyway. No one man builds a spaceship. The Jupiter Icy Moons Explorer has just launched, and it would be easy for me to say that ESA made it. But while that is true, that glosses over the colossal process that took a vague idea on a design board and turned it into a fully realized behemoth of metal and carbon fiber, hurtling up through the atmosphere. Building a probe like JUICE is a massive undertaking. For JUICE, it was a task that involved 18 countries, 60 companies, 11 years, a 5-city tour, and 350.8 million euros of technical expertise, equipment, and resources. By delving into the story of the creation of JUICE, we gain a greater appreciation for the incredible process by which such craft are made. JUICE launched on the 14th of April 2023, but that is only half the story. I'm Alex McColgan, and you're watching Astrum. And it's time to explore the first half of the journey of JUICE, the half that took place before the probe even left Earth. Jupiter's icy moons, Callisto, Europa, and Ganymede, hide a fascinating secret beneath their surface. All are thought to house deep subsurface oceans, some of them larger than the combined oceans here on Earth. These are of immense interest in the scientific community, as such large bodies of water could potentially make these moons habitable. Water and nutrients are two of the key ingredients for life. We have deep sea ecosystems here on Earth that thrive on nothing else. Could microbes also have formed in the depths of the moon's icy oceans? Without more information about those oceans, it's hard to tell. What exactly do they look like? What are their features? What are they hiding? Where is their liquid and where is their ice? By better understanding these icy worlds, scientists can gain insight into how they formed and evolved in the past, and can better predict the odds of life emerging in them and other icy worlds outside our solar system. As such, it was decided on the 2nd of May 2012 that a new mission to explore these moons should be launched. JUICE beat out budget proposals for a new gravitational wave observatory and an advanced telescope for high-energy astrophysics, becoming the European Space Agency's main focus for a large-scale mission over 2015 to 2025. But that decision needed refining. JUICE was still only a partially formed idea. Even once it was decided that Jupiter's icy moons should be explored, the next question was, what scientific instruments should JUICE carry to explore it? So just 28 days after JUICE was announced, ESA reached out to the wider scientific community, asking them what they would like to see on JUICE. In the end, 10 scientific instruments were selected, including cameras with a spatial resolution as fine as 2.5 meters per pixel, spectrometers picking up features down to a resolution of 75 meters, a laser altimeter, and plasma and particle monitors. A magnetometer would study Jupiter's magnetic fields, and an ice-penetrating radar would peer through its surface to see the structures that lay beneath. These parts would be provided from various member states of the European Space Agency, 16 nations in total. Along with them, the US and Japan space agencies would also contribute. Airbus Defence and Space was selected as the primary company in charge of building JUICE. ESA had set the expectations for the mission, but it was up to Airbus to design, develop, integrate, and test JUICE before delivering it to the Guiana Space Center in France to be launched. And it would be no easy task. JUICE would be a solar panel probe working at the limits of how far from the sun solar panels could be expected to function. At 740 million kilometers, sunlight is so dim, it's equivalent to about 3% of what we see on Earth. The panels for JUICE would need to be massive, 85 meters squared, to provide JUICE the power it needed for its various instruments. Those instruments would need to be protected. Jupiter's environment is full of intense radiation, which will damage unshielded components. Passing through its shadow is so cold, temperatures reached minus 250 degrees Celsius. But JUICE would be passing Venus on its way to Jupiter, as part of one of many gravity assists, so it would also need to be able to endure hot temperatures. It was there to study magnetic fields, so its own internal electronics couldn't create magnetic fields able to interfere with its sensors. And as there was a chance it was heading to environments where life could thrive, the utmost care had to be taken that no Earth-based bacteria would be introduced to those environments once the mission was over, and JUICE crashed into the surface of Ganymede. These designs took time, and it wasn't until 2017 that Airbus felt that the designs were complete. Later that year, the first parts started to come to life. One such part was RIME. JUICE is a big craft, and its radar for icy moon exploration is a massive 16 meters long. It would be incredibly sensitive, able to see through 9 kilometers of ice to make out structural details to a resolution of 50 meters. Testing the part involved creating a model version of JUICE and then hanging it below a helicopter, which then flew it over the fields near Friedrichshafen, Germany. I wonder how far into the Earth it was able to see. It must have been a fun sight for any residents in the area. Another model was heat tested in Noordwijk, the Netherlands, at ESA's main facility for spacecraft development and testing, STEC. JUICE's parts would need to endure the freezing cold of space, so technicians there used liquid nitrogen. They had 25,000 liters of it, to freeze the chamber down to minus 180 degrees Celsius. However, JUICE would also be traveling near heat sources, so they simultaneously blasted it on one side with an array of lamps and mirrors, raising the temperature to 200 degrees Celsius. The JUICE model, fortunately, proved capable of enduring these incredible temperature variations. However, these were just models. The true JUICE, the one to be launched, began its life in Madrid. There, in July 2019, its towering 580 kilogram chassis was assembled. You really get a sense of the scale of the probe by seeing the technicians working alongside it. The completed JUICE weighs 5,300 kilograms, although about 3,000 kilograms of that is the chemical propellant it needs to complete its maneuvers. Juice needs a lot of juice. Just a month later, Juice opened its eyes. Its nav cam had been completed in Toulouse, and what better target for it to look at than its eventual destination, Jupiter? The image at this distance is a little pixelated, and the saturation of Jupiter is bright as a consequence of trying to see Jupiter's moons too. But even before it was fully assembled, Juice has already set eyes on its target. But the chassis was not ready to receive its eyes yet. First, it left Madrid, travelling across Europe to Lampoldshausen, Germany. It would receive its thrusters there, one large 400 Newton main engine and 20 smaller thrusters. Next, it took a short trip to Friedrichshafen, where its technical equipment began to be integrated into it. This lengthy process took a whole year, as each piece was carefully added and tested. Balloons were used to simulate weightlessness in space, allowing the massive 10-meter magnetic boom to practice unfolding itself. Like many craft, Juice would need to fold itself in to be able to fit on the rocket that would later carry it into space. But finally, this stage was complete. Of course, this meant more testing was in order. Juice was taken to S-Tech, as it was home to the largest vacuum chamber in Europe, the Large Space Simulator. Getting the large Juice into the even larger LSS was the work of 2 days. Finally though, after carefully transporting using massive crane equipment, Juice began its testing. Meanwhile, its components, such as its antenna, got to try out S-Tech's Blue Room. This unique room is an excellent place to try receiving delicate radio signals. The blue spikes that make up the room do an excellent job of cancelling out all other sounds and stray signals. RIME's 16-meter antenna was scaled down for these tests to about 80 centimeters to take advantage of the facilities by using a more optimal frequency. The tests went well, and within a few months Juice was on the road again. This time it was headed for Toulouse, France. It was drawing closer to its eventual launch site, but it had one more step to make along the way. What probe would be complete without its solar panels? Made up of 2,356 solar cells each, the panels of Juice would also fold up before launch, only extending once the probe was safely up in space. Juice was receiving 10 panels in total, 5 on each side, and unlike the other components, which would be hidden inside protective shielding, these panels would have to endure the heat and radiation of space on their own. They had to be maneuverable, as too much energy could cause the internal workings of Juice to overheat. Power would be regulated carefully. All of this had to be done under the most careful of conditions. Clean rooms were used all along this process to reduce the risk of dust and bacteria getting onto the equipment. Juice was a little behind schedule, so had to be flown into Toulouse, representing one of the first times this had happened. This last stage of integration and testing was evidently not easy, as it was not until January 2023, a year and a half later, that Juice was finally ready. And the rest of the story you may already know. Juice was taken to French Guiana, and on the 14th of April, aboard an Ariane 5 rocket, was launched into space. It will now spend the next 8 years travelling through space, performing 3 gravity assists around the Earth and 1 around Venus. Finally, in 2031, it will arrive at the Jovian system and will begin its careful evaluation of the icy moons there, the awe-inspiring Ganymede, Callisto and Europa. In time, and assuming that nothing goes wrong, the data and answers it will provide may give us insight into whether life could exist under those frozen surfaces. And eventually, in 2035, its mission will come to an end, and it will crash into Ganymede. Its mission hopefully a resounding success. But it's important to recognize just how much of its journey has already taken place before it could leave the planet. Juice represents a huge engineering feat, involving hundreds of people. And while we await with eager excitement the results of this work, it's important to recognize and celebrate the expertise that allowed it to come into being in the first place. If Juice ultimately finds the answers scientists hope for around Jupiter, it will only be because of the great endeavor that took place here on Earth. Looking up to the stars on a bitingly clear night, a horizon away from the nearest town, you'll feel alone. But as your eyes adjust, you are embraced by the light of an entire universe. Surrounded by such scale and wonder, it's hard in that moment to imagine that we are it, isn't it? That we are the only life the universe will ever know, confined as we are on this pale blue dot. Perhaps we are alone. Or maybe, just maybe, given enough time, nature's laws conspire to make life not just probable, but inevitable. I'm Alex McColgan, and you're watching Astrum. Join me today as we explore the chaotic transition from chemistry to biology on our planet, seeking answers to some of the most debated and fervent questions in science. What is life? How could life have emerged on Earth in an environment that would kill us as we are today? And can it begin all over again elsewhere in the universe, or even on our own planet? To begin to answer those questions, let's imagine that while walking across a barren desert, your foot kicks a stone. It wouldn't occur to you that someone put it there or crafted it, since the stone is too simple an object. Now, imagine instead that you stumble across a glistening, precision-made, embossed gold pocket watch. William Paley argued that because, unlike a stone, a watch obviously requires a designer, you'd have to assume that someone had made the watch and placed it there. And because, when you truly think about it, life is far more intricate than a watch, life too must require a designer. It's a compelling argument, isn't it? Even the simplest forms of life are far, far more intricate than a watch, and if a watch requires a designer, surely so must life. Unfortunately, the argument doesn't quite work. But why? What really is the difference between a man-made machine and mankind? Charles Darwin's work on evolution and the origin of species crystallized the idea that life evolves and that all life began from one common ancestor. Therefore, I should infer from analogy that probably all the organic beings which ever have lived on this earth have descended from some one primordial form into which life was first breathed. And there it is, emergence, life from chemistry, something different than the sum of its parts. Darwin understood that life needs no designer. It is able to be more intricate than a watch without a designer because it is a complex, adaptive system driven by natural selection. It has the ability to evolve. A watch is merely complicated. But before we go back 4 billion years to uncover life's genesis on Earth, we should probably all agree on what it is we're looking for. What do you think defines life? What makes something alive? If you're struggling for an answer, don't worry. Even NASA can't get 3 words into their definition without being challenged. This is science at the bleeding edge. NASA defines life as a self-sustaining chemical system capable of Darwinian evolution. Prominent scientists argue that life is not strictly self-sustaining. Life requires an environment with which it has a dynamic relationship, where life draws its energy and raw materials and expels its waste, an environment that is full of free energy, an environment that sustains life. Life's relationship with its environment is crucial to understanding how life is possible. You see, life is, at first glance, in defiance of the second law of thermodynamics. How does the beautiful design of a bacterial cell, with its incredible complexity, control, and order, seemingly defy entropy and emerge out of a structureless chemical soup? According to the second law, entropy should always increase, and systems should get more disordered with time, not less. It was Erwin Schrödinger who realized that it is the environment that picks up the thermodynamic cost in his book, What is Life, in 1944. On closer inspection, when we include the environment that sustains life, entropy does increase overall. The second law of thermodynamics is not broken. In fact, entropy increases faster with life than without. It is this that led Jeremy England, a professor at MIT, to say, You start with a random clump of atoms, and if you shine a light on it for long enough, it should not be so surprising that you get a plant. Life is incredibly effective at transforming energy and increasing entropy. How effective? Let's compare it to the brightest and most powerful object in the solar system, the Sun. In just 58 microseconds, it produces more energy than our species has in its entire history. Pound for pound, though, humans output a staggering 6,000 times more power at rest than the Sun. Despite creating extremely localized order, life degrades free energy to heat, increasing entropy in the universe overall. Unsurprisingly, given that you're watching this video, it's clear that entropy allows for, or even encourages, the development of life. So how did the building blocks of life seemingly defy entropy in constructing order from chaos? How does a living cell build up that can power itself, encode itself with DNA, construct itself too, and have the ability to evolve? And how can it do it all piece by piece while being functional at every step, even though each part is essential? How on earth could life emerge? Well, there is little consensus on the precise way that life actually emerged on Earth, but let's explore the molecules that, without exception, build every single life form on Earth. Perhaps life offers clues to its own origin. The key basic building blocks life uses today, in no particular order, are fatty acids, amino acids, and nucleotides, and all three are believed to have been present on the early Earth, and have even been found on asteroids in our solar system. The first are fatty acids, and despite having little chemical functionality, they create structure and have an extraordinary function built in. These long chain molecules make up cell walls of all life on Earth and are believed to have made the first membranes of protocells. Membranes are barriers and fundamental to create an individual unit. After all, you can't have a house without walls or a country without borders. That's not a political statement. Remarkably, cell-like structures made from fatty acids form spontaneously in water. As anyone who's failed to make a simple mayonnaise will know all too well, oil and water don't like to mix. These fatty acids, with a water-loving head and a water-hating tail, will spontaneously arrange to minimize water's contact with the tail and maximize it with the head. These simple pressures can create a bilayer membrane with a cavity for an early cell to call home. This is called a liposome. Unbelievably, these liposomes can also spontaneously divide and speed up chemical reactions by encapsulating and concentrating the molecules in a smaller space. This is a perfect example how unexpected lifelike behaviors can emerge out of the laws of quantum mechanics. But won't these crude divisions just go wrong and kill the cell more often than not in a hot, salty water? Well, yes, there's a good chance. However, the environment isn't a simple system. It's impure. There are other molecules floating around that can stabilize the cell walls further, like amino acids. A diverse range of these building blocks were present on early Earth and are even present in our solar system. Today, life uses 20 different amino acids to make all the cellular machinery within us, like enzymes and ion channels, as well as larger structures like muscle and hair. There is a miraculous relationship between amino acids that make up proteins and our next building blocks, nucleotides. A relationship that is important in helping us to understand how life's informational system may have emerged. The ability of life to create and store information is achieved by nucleotides, which are present today in RNA and DNA. RNA is believed to be involved in the origin of life because short chains of RNA serve another simpler purpose. They can also catalyze some chemical reactions, which perhaps kick-started life's early chemistry. Nucleotides have other functions too, and feature in several vitally important molecules like ATP and ADP, the pair of molecules that drive work in a cell, acetyl coenzyme A, and vitamin B12. In fact, every living cell today relies on what's known as the central dogma. DNA is translated to RNA, which encodes proteins. This is strong evidence that all life on Earth can be traced back to one life form, LUCA, the last universal common ancestor. The central dogma is a highly evolved system that has redundancy and error correcting built in. But the ability of RNA to encode proteins may have much simpler beginnings, one that doesn't require enzymes, one driven in part by the same physical pressures as fatty acids forming a cell-like structure, a mechanism that could have introduced information to protocells. You see, different RNA bases can encode specific amino acids. This means that a random string of RNA in early protocells could have produced a non-random string of amino acids, which could have conferred an advantage to the protocell containing it. Perhaps the amino acid stabilized the membrane, and it would have been more likely to survive and divide, potentially reproducing that information and passing it on. So now we have a great primordial soup of molecular potential. We have the thermodynamic encouragement for life, self-dividing cell walls and short RNA strands that could have encoded functional amino acids. How can we get past this primordial soup of small molecules for life to emerge? Well, we also need the one mechanism that is crucial to all theories: selection. Without selection pressures, in 14 billion years, molecular complexity wouldn't have moved much past basic molecules like these, let alone a complex enzyme, because you'd be relying on random processes with very low probabilities. Very much like shaking a bag of Lego bricks together for a few years and expecting a perfectly formed Death Star to pop out. As the size of a molecule grows, the space of possible configurations grows absurdly quickly, and the probability that even one specific molecule can be made in a useful quantity by chance falls to near zero. And that's just for one molecule, let alone a gold pocket watch. The creationists may have a point. Incredibly though, research suggests that the proposed chemical reactions on early Earth were capable of a kind of evolution way before they transitioned to life. Some chemical reaction pathways can produce molecules that catalyze the pathway itself. These are known as autocatalytic. This catalysis increases the flow of resources through one pathway, potentially away from a competing pathway, and therefore increases the first success. When these pathways loop around on themselves, they are known as autocatalytic sets. These are nascent forms of metabolism. Crucially, these metabolisms are spontaneous and can exist without the need for evolved enzymes. We have seen how the molecules present on early Earth interact and produce lifelike behaviors without the need for the highly specialized cellular control. Much of life's chemistry may indeed be spontaneous. Metabolism, chemical selection, division, information transfer, but in order for life to emerge and for all these processes to come together, we need time. But incredibly, not much time at all. The Earth formed around 4.54 billion years ago. The Moon was created 4.5 billion years ago. There were liquid oceans around 4.4 billion years ago, and the earliest life is present potentially as early as 4.3 billion years ago. For something regarded by many as unlikely, it's curious, don't you think, that almost as soon as it is given the chance, life emerges. Maybe life is inevitable. At least it was on the early Earth, because Earth has a lot of free energy and is, in effect, a giant battery. Some 4 billion years ago, our ocean was acidic and lacking in electrons, while the molten mantle just below it was alkaline and rich in electrons. A huge chemical charge imbalance that has been shown to be used to power chemical reactions that are evolving towards life. There is a consensus that somewhere on this world, where the inside of the Earth meets the outside, where the two ends of the battery meet, there was a spark of some sort. There are deep sea hydrothermal vents, gas-filled caves, hot springs, evaporating pools, and volcanic areas totally devoid of oxygen. All have all the elements that we think are required for life to emerge to harvest this free energy source. And all would have killed us if we were able to travel back in seconds. It is proposed that LUCA was a methanogen, originating at one location like these, an organism that reacted hydrogen with carbon dioxide to make methane. That's partly why a form of life evolving from scratch now is considered to be impossible because of the oxygen concentration. Add oxygen to hydrogen, and instead of life, you've got rocket fuel. We may never know for sure if a form of life existed before our central dogma ancestral line, but that's not to say life hasn't emerged elsewhere in our galaxy or even our solar system. Planets have been found nearby in our galaxy that are similar to Earth and could replicate the conditions of the early Earth. Our planet is not so special. Given the thermodynamic pressure for the emergence of life, it seems as though life on another planet is an inevitability. There is volcanic activity on moons orbiting Saturn and Jupiter, providing a similar environment beneath the surface to Earth too, which is why scientists are so interested in exploring the icy moons orbiting our nearby planets. Hydrogen-rich volcanic plumes, just like those from our deep-sea vents, have been observed erupting from the surface of Saturn's moon Enceladus. Despite the extreme speed with which life appeared to emerge on Earth, the time to go from single-celled to multi-celled was 1.5 billion years. It's clearly a hard jump in complexity to evolve communication and cooperation between cells, let alone interplanetary communication with alien life forms. So, although we haven't found signs of life elsewhere yet, absence of evidence is not evidence of absence. With all this, looking up to the stars, the way all these molecules work together, it's hard to feel alone in the universe. The early Earth seemed ideal for life to emerge, but then, even if it was less hospitable, there is always a chance. As Dr. Ian Malcolm said in Jurassic Park, life, finds a way. Thanks for watching. I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.